Hello, everybody. So today's subject is going to be spin. Now, spin is one of those concepts in quantum mechanics that give us multiplet structures, okay? And the question that we're going to ask is why? Why does spin come in multiplets or pairs, or why does spin, split energy levels in our observations? And the answer is going to lie in the interplay of the ideas of symmetry, as always. So we'll think about, rotational symmetry. We'll think about rotational symmetry playing the role of determining the possible internal states. Okay? And then we'll show all of these. The next one we're going to show is time reversal symmetry. And what time reversal symmetry is going to show us is certain states are forced to be degenerate. Right? That is true. And lastly, symmetry breaking. And symmetry breaking, sorry, kind of tweaking out. Symmetry breaking comes from external fields. So the symmetries that get broken, they reveal underlying multiplet structures. As these they indicate these spectroscopic lines. So that's the importance of spin. Spin is going to allow us to see the forcing of these multiplet structures from just the algebra of rotations, from time symmetry, time reversal symmetry, and then these external fields, like applying a magnetic field in somewhere inhomogeneously, or even just homogeneously. It'll give us these notions of spectroscopic lines, like Zeeman splitting, etc. So that's what we're going to get into today. And so what we'll first start with is just, in quantum mechanics, the angular momentum operators. So the angular momentum operator is usually denoted with J. You'll have Jx, Jy, and Jz, and they satisfy they satisfy the Lie algebra of SO3 and their commutation relations, where you have some Ji and J sub j as IH bar with the cyclical Levi-Civita tensor with J sub k. And what we can do is define similarly, as we did previously, the ladder operators with J plus 1, it's equivalent to Jx plus or minus IJY, and these ladder operators are going to obey Jz with J plus or minus. The raising and lowering operators are going to be equivalent to plus or minus H bar J plus minus, and same thing, J plus with J minus. They're going to give us 2 H bar J sub Z. And what we can do is build out the multiplet. Okay, so because j squared is equivalent to jx squared plus jy squared plus jz squared. This commutes with j sub I. And what this allows us to do is simultaneously diagonalize j squared and jz. So let's let their eigenstates be expressed by their index j comma m. And so if we have j squared acting on j m, this should give us h bar squared lambda, some eigenvalue j, with this state. All right, and then if we look at how jz acts on jm, this should give us h bar squared m to jm here. And these ladder operators are going to shift this m value here. So from the commutators, what we can have is that jz acting on j plus minus with these ladder operators, that should be equivalent to j plus or minus 1 h bar j plus minus acting on jm state, acting on the jm state. So what j plus does, again, as ladder operators do, is it's going to raise m by 1 unit, and then j, lowers it, right? So that's essentially what's happening. And in a finite dimensional representation, there has to be some top-weighted form, or sorry, some top-weighted, highest weighted state, psi sub top, that is annihilated. I think annihilated has 2 ends. I don't know. Annihilated. It should be annihilated by the raising operator. So we should be able to raise this top state essentially into nothing. And labeling the state by its maximum value, m is equal to j, we would have that at the maximum value, the state itself is j. Now we can come back to our Casimir operators by taking this by thinking about this representation with the raising and lowering operators. We can take j plus and j minus and mix them such that we have jx minus I jy as products of each other, I jy. So we have minus and plus, right? So the raising and lowering one. And if we were to distribute that out, that would just be jx squared plus jy squared plus I times the commutator. Hopefully that's obvious to you. Plus the commutator of j and y, which essentially is going to give us jx squared plus jy squared minus h bar jz. Hence, we can have that the square of the angular momentum is equivalent to this plus jz squared plus h bar jz. Now what we can do is apply this to the highest state to see what we can get. And so coming back over here, we can have j squared is j comma j, j squared acting on j comma j would be equivalent to this identity that we just derived plus h bar jz j comma j, and that should give us, since this guy is going to go away, we can just have that as 0 h bar squared j squared, and then plus h bar squared j with j comma j, and that should equal h bar squared j plus 1 if we simplify this out, j comma j. And because we have this j squared, this j plus or minus commuting together, that means that all the states in the representation, they share the same j squared eigenvalue. Therefore, every state in the multiplet j squared of jm, that should be equivalent to h bar squared j plus 1 j comma m here, where m itself can be minus j plus 1 all the way down to j minus 1 to j itself. All right, so it's kind of this increasing thing. All right, and every single state in the multiplet will satisfy this particular relation. So that's what we've derived. And now for the smallest non-trivial case, we can have j to be equivalent to 1/2. And when we do this, j squared will be equal to h bar squared 1/2 times, 1/2 plus 1, which is 3/2. So that should equal 3/4 h bar squared, right? Just kind of plugging that in. And m here will be plus or minus 1/2. So the system actually, what happens here is it actually possesses two states. So we can denote state, we can denote the spin up state as m is equal to plus 1/2, right? And then we can also denote the m equaling minus 1/2 as the second state. And this is the spin 1/2 multiplet. So it's this is a fundamental representation of the rotation group. So the physical idea here is that rotational symmetry doesn't just allow spin, right? Rotational symmetry, rotational, if you speak Greek, rotational, that's funny. Anyways, the rotational symmetry, it forces the internal states to be organized into multiplets. So forces internal So that's an important fact, because the total angular momentum, J, right? Your total angular momentum labels the multiplet, and the projection M runs it runs over 2J plus 1 values, or discrete values. So for J is equal to 1/2, we get the up-down pair purely from the representation theory of the Lie group SO3. Okay? Just purely from the Lie, or the Lie algebra, the Lie group. The Lie group is the manifold of the rotation group. The Lie algebra works with the differential operators and commutation relations. Okay? So, hopefully, this was a little bit messy, but hopefully that makes sense. Now, what we can do is talk about, we started with rotational symmetry. Now let's look at time translation symmetry, and what we can do here is we can make another page. Now, time translation symmetry. This is going to force something called Kramer's degeneracy. So time reversal is a anti-unitary transformation. So it's anti-unitary T that reverses angular momenta. Okay, so if we have T with J and then T minus, this has the property of taking the angular momentum operator and reversing it. So for spin 1/2 system, you can explicitly represent the time translation or the time reversal operator as e to the minus pi, sy for whatever basis that you're choosing to represent spin with, times k. This will just be the complex conjugation in the standard spin basis for z. And you would have, of course, the Pauli matrix, the second Pauli matrix, with this. Okay, so this representation is also interchangeable. Now K is the complex in the SZ basis. Okay, just to be clear. Now the crucial property for half integer spin is that if you do time translation symmetry twice, you'll get the identity but inverse. So for integer spin, if you were to do a time translation operator twice, that would just give you the plus identity. So this distinction is very vital, and this is property of half integer spin for integer spin. All right, so that's just true. That's how time translation works. Now, if we assume the Hamiltonian is invariant under time reversal, so let's say the time translation operator looks like this, to give us an invariance, we can play around with the psi en energy be an energy eigenstate with eigenvalue E. So then we have that the Hamiltonian operator with the time translation operator acting on the wave function, that should be equivalent to T times the Hamiltonian operator acting on the wave function, which would give us the energy eigenvalues. Okay, that should be true. So thus this time translation operator, this is also an eigenstate. Okay, it's also an eigenstate, and it's with the same energy as the E eigenstate, or as the E eigenvalue. So it remains to see whether psi and t of psi, or t acting on psi, are actually distinct from each other. So are they distinct? What we can do is try to compute their overlap using anti-unitarity. So if we take, let's say, the state T alpha and the state T beta to be equivalent to the inner product of beta and alpha for the overlap, what we can do is set alpha to be equivalent to psi and set beta to be equal to t acting on psi. Then what we'll have is that t acting on psi is equivalent to t, or sorry, we'll have t psi with t acting on t psi. That shouldn't be a, that should be a comma. Sorry, parentheses. So we can apply the translation operator twice. And since we have that t squared is equivalent to negative I, right? And this is for half integer spin. Then we can have that t squared is equivalent to minus psi. Hence, one can have that we should reverse the wave function but the anti-unitarity property, what that also is going to do is it's going to give us t psi with t acting on t to be equivalent to t psi star. Actually, there might be a more straightforward route to this. You know what? Let's do this, because I think this is going to be complicated. So what we can do instead, sorry, just to switch up on this. I don't feel like editing this out though. My mistake is that I'm not being careful with the phases of the wave function. So what I need to do is let's try to evaluate this by, let's insert t dagger t is equal to I and use maybe some let's use some dummy variables where we say that this is equivalent to chi phi, and then we want to choose, we're going to want to choose phi, a phi ket such that it's equivalent to the wave function, and a chi ket that gives us the translation operator. Okay, that should be a little more straightforward. So that then the translation operator, then if we double apply it, that should give us this. But if we remember that t is equivalent to t squared of psi, which should reverse the wave function, then the left side is going to be, the left side of this equation is going to be minus t psi, which is equivalent to t psi. And so what that leaves us with is that the only way for this to be true is that t psi must be equivalent to 0. So we've set it up in such a way that that psi and t acting on psi are actually orthogonal to each other, right? They actually have to be orthogonal. And since they share the same energy, so we have orthogonality, right? So we've concluded orthogonality between the time reverse states, and also what else we have is that they share the same energy. So every energy level, since they share every energy level, we can conclude that every level is at least twofold degenerate. And this is called Kramer's degeneracy. Okay? So the physical idea is that the time reversal is going to flip all of the angular momenta here, and it roughly maps this spin up state to a spin down state, up to a phase, of course. And in a time symmetric world, the two orientations must have identical energy. So for half integer spins, the algebra then forces them to be distinct orthogonal states, so the degeneracy is protected as long as if time reversal symmetry holds, then we have this algebra that forces them into distinct orthogonal states that share the same energy. Thus, that's what creates the twofold degeneracy. And it's kind of like it's a degeneracy that gets protected by this time reversal symmetry, as long as it's held. Now, this leads us to the idea of symmetry breaking. So what we can do first is construct something called the Zeeman Hamiltonian. So now let's introduce a static magnetic field B, so we'll say B0, and the magnetic moment is mu of gamma acting on S, with this gamma being the gyromagnetic ratio. Now the interaction energy it should be minus mu dotted with the B field and give something like the gyromagnetic ratio with the Z component of the magnetic field along the spin vector. And then for spin 1/2, this spin basis vector will just be h bar over 2 times the Pauli matrix for Z. Hence, what that will give is the Zeeman Hamiltonian That's just the gyromagnetic ratio, B over 2 times 1 minus 1, 0, 0. Okay? So it's just a 1 and a negative 1 on the diagonal, because that's like the basis for the z direction. Now, the eigenstates here, plus 1, or sorry, spin up, and the spin down, the SZ eigenstates, their energies are going to be, they're just going to be the negative and positive versions of themselves. So for spin down, the spin down energy will be B squared over 2. And then the splitting between both of the states, let's just say it's going to look like delta E, which is the magnitude of the gyromagnetic ratio with B and H bar. So really the transitions between both of these levels are going to be induced by photon of frequency delta E over, sorry, not delta W, delta E over H bar with the Lamour frequency times B naught times the strength of the magnetic field. And this is what we call the Lamour angular frequency. Okay? So what physically happened? What physically happens in Zeeman splitting is that the magnetic field picks this preferred direction in the Z component. And this preferred direction to spin, or this preferred direction in space, is going to couple to the spin. Okay? So because it's coupling to the spin, it breaks time reversal symmetry. So in other words, this interaction means that the Zeeman Hamiltonian is not unchanged after the time reversal symmetry. So because the time reversal symmetry acting on the spin state, or on the spin basis vectors, we have that they reverse it. So while B remains unchanged. So the symmetry that protected Kramer's degeneracy, in other words, the symmetry that protected Kramer's degeneracy, is now gone. And so those two states now are going to drift apart in energy. And that's exactly what's happening here. So Zeeman splitting just directly exposes the underlying spin multiplet. Without the field, we only knew there were two states, but they were energetically indistinguishable. So the field now is choosing, the magnetic field here is choosing to label their states here. It's choosing to label their states by their orientation and turn this this representation theory into this measurable spectral line. So if you've ever seen Zeeman splitting, you'll have the energy level here, and then you'll have basically you'll have that this is dark, and then you'll see the rings of light. If you've ever played around with a Zeeman, with a electromagnet, and looked through to see the Zeeman splitting happening as you turn the magnet on, that's basically what happens. It's a pretty cool thing. I would recommend people go touch grass and play in a lab and watch it happen in real time, which I was lucky enough to do. We actually built the experiment, so it was pretty fun. Or assembled the experiment. But anyways, so you have rotational symmetry, again, that comes from determining the internal states. Its algebra forces the finite multiplets, with the Casimir operator being the square of the angular momentum, just being j and j plus 1 with h bar, and then the projections with m. Okay. And these m projections play around, and this j 1/2 is going to yield this nice two-state spinner. And what the time reversal symmetry is going to force is the states to become degenerate pairs for half-integer spin, and then the anti-unitarity nature is going to guarantee these orthogonal partners with identical energy that's protected as long as the Hamiltonian is T invariant, okay, or just time translation invariant. The external magnetic field that's applied to this system will break the time reversal symmetry, and the Hamiltonian now actually distinguishes. The Hamiltonian itself likes to distinguish between these two orientations, and it splits these formally degenerate pairs by the amount proportional to the field strength. So in a way, rotation in physics tells you what states are actually allowed to exist. The time reversal is going to tell you, basically what states must share the same energy. Okay? So it tells you which states share that same energy, and then a magnetic field will just reveal the multiplet by that lifting that degeneracy so that they're visible. So in a spin 1/2 system, the smallest realization of this connection between group theory and symmetry and experimental spectroscopy, when we measure a Lamour frequency, the Lamour frequency basically just shows us the representation theory of the rotations made manifest. All right? So that's everything that I have for you today. Let's see, what are we going to do next time? Let's check it out. We might do let's see. I'll leave it as a surprise. Okay, see you guys next time. Bye-bye.